Well, section 15.5 is about finding the center of mass. So if you have some object and you want to be able to balance it, then if you can find a line this way where it balances, look, it balances all by itself. Right. Ah, there it is. Ah. And then you find a line this way where it balances left and right. Then where those two meet, that's the center of mass. And then you could just take one point like a finger, put it underneath, and look at that. With just one finger, it balances perfectly. Okay, well, I was cheating a little bit. So that's the idea of center of mass. And that was covered in Math 3B. We're going to do it now in Math 3C, because what if the object is not the same density all the way through? So maybe this part is much lighter than this part because these have the keys. So then we'll have a density function that tells us how much it weighs per square inch or something like that. So take a square inch, how much is that part going to weigh compared to what's the density over here? So this is the object, that's the graphing calculator. So that's going to be the region, and we're trying to find the center of mass. And you might think, well, center of mass, I would estimate the center is right there. And you could be completely right if this is a uniform density all the way throughout. And in Math 3B, that's what we said. This is a uniform density all the way throughout. But if these red lines are much heavier than these red lines, instead of the center being here, it would have to be moved over here if these lines are heavier than those. So suppose that the region R has a density function rho at every point x and y. So this function will tell you how dense it is no matter where you are in the object. So first of all, you need to find the total mass. And the total mass is going to be do the double integral over this region of the density function. And then you could do dx dy or dy dx. Now, like I was doing with the calculator, we need a line like this called the moment. So we need a moment about the y-axis and a moment about the x-axis. So the moment about the y-axis. So this will be my, or it's called my. And then you do the exact same double integral. Except this one is multiplied by x. Then the moment about the x-axis. So that is called mx, and that's going to be the exact same integral, except it's multiplied with y. And then for the center of mass, so that's going to be the point x bar comma y bar, where x bar is equal to my divided by the total mass, and y bar is going to be mx divided by the total mass. So the best part of this whole thing is, for each problem, we get to do 3 triple integrals. Sweet. So for example number 1, so the region is defined by y equals the square root of 4 minus x squared. The density is directly proportional to the distance from the x-axis. So not only do we get to do 3 triple integrals, but we have to find out what this function is talking about. So if you were at some point, let's say this point is x comma y, then the distance from the x-axis, that would be this distance right here. So that distance is whatever the y equals. Directly proportional means it's a constant times that. So that means the density function at x comma y is going to equal some constant times y. So basically what that's saying is on the x-axis, it has a density of 0. When you move up to a height of 1, then everything has a density of 1, like 1 pound per square inch or something like that. You move up to 2, and now it's 2 pounds per square inch. At 3, it's 3 pounds per square inch. So it's getting more and more dense as you go up. That's what this part is saying. All right, now we're ready to do the integrals. So for the mass, so you could either write out the word mass or just use capital M. So that will be a double integral. And then we're integrating the density function. And now we need to set up the limits of integration. So this thing, if you square both sides and you move the x squared to the other side, it's going to say x squared plus y squared equals 4. So that would be a full circle. But because it's only using the positive square root, that means that it's the top half of the circle with the radius of 2. So this is the region that's being talked about. So let's see. Since this has a y, I think I'm going to go ahead and do dy first and then dx later. So the y value. So if you are at some point, then the y value, like it could go from the very smallest, that would be a y value of 0. And then this is when it reaches the function. So that would be when y equals this square root. So it would go from 0 to the square root of 4 minus x squared. And then for x, you can see on the x-axis, x is going from -2 to 2. And then actually integrate this thing. So this is going to be y squared over 2. That gets evaluated from 0 to the square root of 4 minus x squared. And then when you substitute this in there, the square and the square root are going to cancel each other out. And with this 1/2, I'm going to factor it out. So the square and the square root will cancel, so all that's left is 4 minus x squared. Somewhere along the way, I lost the k. So the k should have been right here. And then because k is a constant, you could just factor that out. And then when you substitute 0, that's going to be 0 squared, so that does not contribute. And then integrate with respect to x. So this will be k over 2. The antiderivative will be 4x minus x cubed over 3. And then that gets evaluated from -2 to 2. So k over 2. And then when you substitute the 2 in here, this is going to be 8 minus 8 thirds. then minus, when you substitute the negative 2, this will be negative 8. And this will be negative 8, but because of that, it's going to become positive 8/3. So this negative is going to turn that one into a positive, so that's going to make it a 16. And then this negative will make that one negative, which means we have negative 8/3 and another negative 8/3, which means negative 16/3. So then it is 16 minus 16/3, which is 32/3. And then if you take that 32/3 and multiply it with this on the denominator, it's going to be 32/6. And then that could be reduced. So if you divide that by 2 and change that to a fraction, 16 divided by 3 sounds right. So k times 16 divided by 3. And then remember, that's the m, the mass. And that means we are 1/3 done. So example number 1 continued. What about the moment about the y-axis? So this one will be the same double integral. And it's still going to have the k times y. And then I think I'll still do dy and then dx. And when this is the moment about the y, this has an extra x in it. Okay, so start integrating. So this k is a constant. I could factor that out. And then we're integrating with respect to y, so this is going to become y squared over 2. This x is being held constant, so it just stays there. And then evaluate that from 0 to the square root of 4 minus x squared. So the k is still factored out. The x is still just going to wait there patiently. And like last time, when you substitute the radical in there, it gets rid of the radical. And this little divided by 2, I'm going to factor that out as well. All right, so this is going to be 4x. And when you integrate 4x, that's going to be 2x squared. This is going to become x cubed, so when you integrate that, it's going to be x to the 4 over 4. And then evaluate from negative 2 to 2. Now this one should equal 0. When you have odd powers and you use a number and it's negative, then basically these things get doubled. So the 8 got doubled, the 8/3 got doubled. But when you have an even exponents, then the negative, when you raise it to the 4th or when you square it, it's going to get canceled, and so this should equal 0. Let's see, so the k over 2 is factored out. When you substitute a 2, that's going to be squared as 4, times 2 is 8. And then 2 to the 4th is 16 divided by 4, so that's a 4. And then minus, when you substitute the negative 2, it's going to get squared, become positive 4, times 2 is 8. And then when you take a negative 2 and raise it to the 4th, it's also going to be a positive 16 over 4. So then it's going to say minus 4. And then it's going to say 8 minus 8 is 0. Negative 4 and positive 4 is 0. So this one is 0. All right. Now we're 2/3 done. So the next integral is going to be the moment about the x-axis. So for example number 1, continued some more. The moment about the x-axis will be the same double integral except when this says moment about the x-axis, then you need to multiply by an extra y. And then there would be the density function, and then I'm going to go dy dx. So for this one, you put these two y's together, that's going to be y squared. And then integrate y squared, that's y cubed over 3, evaluated from 0 to the square root of 4 minus x squared. And I could factor the k out. Then for the next step. So when you substitute this in there, it's not going to cancel this time because now it's cubed. So it's going to be 4 minus x squared is raised to the 3/2 power. And then this 3, I could factor it out. It's going to be k over 3. And then integrate from -2 to 2 with respect to x. Okay, well, this problem already has taken long enough. To do this one properly, we would actually need to do trig substitution, and it would take another several pages. So now I'm going to cheat and use the calculator. So let's see. So this part, I'll just leave that there. I'm just going to do this part on the calculator. So first of all, pretend like you're going to graph it. 4 minus x squared is raised to the 3/2. And the window needs to go at least from -2 to 2. I'll have it go -3 to 3. And then the y value, I don't know, so I'm going to put -10 to 10. And the graph looks like a bell-shaped curve. And then integrate from whoops, I thought I put integrate, number 7, from -2 to +2. Oh, I guess my little scale down here are not going by 1, but it is right there telling me it went from -2 to 2, and I got 18.85. And then 18.85 divided by 3 is a 6.283. All right, now we're almost done. So that is the mx. And then the last part is this right here. So x bar is the my divided by the mass. So my, that was 0. And the mass was k times 16 over 3. So that is equal to 0. And then for the y bar, that is the mx divided by the mass. So that's going to be k times 6.283 gets divided by k times 16/3. And then the k's will cancel. And 6.283 gets divided by 16 thirds. It's a 1.178. So finally, my answer on this one is x is a 0 and y is a 1.178. Now go back to the very beginning. Here's the picture of the region we're talking about. So where's the balancing point? Well, because it's symmetric on the left and the right, then it should be right in the center. And also, with the density function, it said that it all depends on the y value. So if you're over here and you go up by 1 or 2, then its density, if you went up by 2, its density is 2. If you're over here and you go up by 2, its density is 2. So it's symmetric on the left and the right. So that means that x equals 0, that part sounds right. Now if it goes up to a height of 2, 1 would be right here. And basically, it's getting more dense as it goes up. And if it's more dense, you actually need to put the point a little bit farther towards the denser part. So to me, this 1.178, that sounds pretty good. All right, now let's work on example number 2. So there's this nice little arc right here. I made a pretty little rainbow. It's actually the top half of a circle radius 1, the top half of a circle radius 3. And the density at any point, so if there's some point right here, x comma y, then the density is proportional to the distance from the origin. So we need the length of this line right here. So you could draw a little right triangle, do the Pythagorean theorem, and you'll find out that the distance from the origin is the square root of x squared plus y squared. And then proportional means that it's a constant times that. And then that's going to be the density function. And next, find the center of mass. So one thing we need to do is the integral for the mass, which will be double integral. And then we just integrate this thing. K times the square root of x squared plus y squared. Dx, dy, or dy dx. That is a perfect candidate for changing to polar, because x squared plus y squared equals r squared. Take the square root of that. That means we're just going to be integrating k times r, and then when you change to polar, it's r dr d theta. And it's nice that we're using r because setting up the limits will be easy. This is a circle radius 1, this is a circle radius 3. So the limits go from 1 to 3. And because it's the top half of a circle, the angle will go from 0 to pi. Now integrate. So this is r squared. The antiderivative of that is going to be r cubed over 3, evaluated from 1 to 3. And you can save time by doing the other integral at the same time. So it's going to be the antiderivative of d theta, so that's just theta, evaluated from 0 to pi. And don't let me forget this little k right here. So this is going to be 3 cubed over 3 minus 1 cubed over 3. And this will just be pi minus 0. So 3 cubed over 3, that's 9. It's 9 minus a third. 9 minus a third is 8 2/3. Nine minus a third, or 26 thirds. So that would be 26 thirds times pi. All right, then on to the next integral the moment about the y-axis. So this will be the double integral of the same thing, but when this says y, it has an extra x in it. And again, I'll change to polar. So in polar, x is equal to r times cosine. And then this square root becomes just r. And then there's r dr d theta. And again, the r goes from 1 to 3, theta goes from 0 to pi. So putting all these r's together, that's r cubed. So the antiderivative will be r to the 4th over 4, evaluated from 1 to 3. I keep forgetting the k. The funny thing is, at the end, the k cancels when you divide at the very end. So I don't really even need to bring the k, but I feel like I must. All right, then on to the antiderivative of cosine is sine. That gets evaluated from 0 to pi. So then we'll have 3 to the 4th over 4 minus 1 to the 4th over 4. And then this part will be sine of pi minus sine of 0. Well, sine of pi is equal to 0, which is what my brain was trying to say right there. Sine of pi is equal to 0, and sine of 0 is equal to 0, so that means this is 0 times this. It means that it equals 0. All right, then one more integral. So for mx, it is the double integral of the same thing, but when this is x, it has an extra y in it. And then we'll change to polar. So in polar form, y is equal to r times sine of theta. And then don't forget the k. The square root becomes r, and dx dy becomes r dr d theta. And of course, there's the same limits. So once again, this is r cubed, so the antiderivative is r to the 4th over 4, evaluated from 1 to 3. Then the antiderivative of sine, so that is negative cosine, evaluated from 0 to pi. So this one is 3 to the 4th over 4, minus 1 to the 4th over 4. And then negative cosine of 0 minus negative cosine, oh no, I switched them. Sorry, pi, and then cosine of 0. So this cosine of pi is negative 1. Together with that, we now have positive 1. Cosine of 0 is positive 1, and because of these two negatives, it's going to be a positive 1, and a positive 1 makes a positive 2. And then 3 raised to the 4th divided by 4 minus 1/4 is equal to 20. So finally, this one is 40. Now for the center of mass. So the x bar will be my, which was 0, divided by that m, which was k times 26/3 pi. And then because it's 0 on top, that equals 0. Y bar is going to be 40, I forgot the k again. Why didn't you guys tell me? Okay, so 40k divided by k times the 26 thirds pi. And this is where the k's can cancel. And then finally, it is 40, I guess didn't need that parenthesis, divided by 26 thirds pi, and then that does need parentheses. So 1.469. So the point is 0, 1.469.